stimulated emission is the process by which an incoming photon of a specific frequency can interact with an excited atomic electron, causing it to drop to a lower energy level. The liberated energy transfers to the electromagnetic field, creating a new photon with identical phase, frequency, polarization, and direction of travel as the photons of the incident wave. This is in contrast to spontaneous emission, which occurs at random intervals without regard to the ambient electromagnetic field. Further calculation can be obtained by statistical mechanics. However, the process is identical in form to atomic absorption, in which the energy of an absorbed photon causes an identical but opposite atomic transition from the lower level to a higher energy level. In normal media at thermal equilibrium, absorption exceeds stimulated emission because there are more electrons in the lower energy states than in the higher energy states. However, when a population inversion is present, the rate of stimulated emission exceeds that of absorption, and the net optical amplification can be achieved. Such a gain medium, along with an optical resonator, is at the heart of a laser or maser. Lacking a feedback mechanism, laser amplifiers and superluminescent sources also function on the basis of stimulated emission. Stimulated emission was a theoretical discovery by Einstein within the framework of the old quantum theory, wherein the emission is described in terms of photons that are the quanta of the M field. Stimulated emission can also occur in classical models, without reference to photons or quantum mechanics. Overview. Electrons and their interactions with electromagnetic fields are important in our understanding of chemistry and physics. In the classical view, the energy of an electron orbiting an atomic nucleus is larger for orbits further from the nucleus of an atom. However, quantum mechanical effects force electrons to take on discrete positions in orbitals. Thus, electrons are found in specific energy levels of an atom, two of which are shown below. When an electron absorbs energy either from light or heat, it receives that incident quantum of energy. But transitions are only allowed between discrete energy levels such as the two shown above. This leads to emission lines and absorption lines. When an electron is excited from a lower to a higher energy level, it will not stay that way forever. An electron in an excited state may decay to a lower energy state which is not occupied, according to a particular time constant characterizing that transition. When such an electron decays without external influence, emitting a photon, that is called spontaneous emission. The phase and direction associated with the photon that is emitted is random. A material with many atoms in such an excited state may thus result in radiation which has a narrow spectrum, but the individual photons would have no common phase relationship and would also emanate in random directions. This is the mechanism of fluorescence and thermal emission. An external electromagnetic field at a frequency associated with a transition can affect the quantum mechanical state of the atom without being absorbed. As the electron in the atom makes a transition between two stationary states, it enters a transition state which does have a dipole field, and which acts like a small electric dipole, and this dipole oscillates at a characteristic frequency. In response to the external electric field at this frequency, the probability of the electron entering this transition state is greatly increased. Thus, the rate of transitions between two stationary states is increased beyond that of spontaneous emission. A transition from the higher to a lower energy state produces an additional photon with the same phase and direction as the incident photon. This is the process of stimulated emission. Mathematical model. Stimulated emission can be modeled mathematically by considering an atom that may be in one of two electronic energy states, a lower level state and an excited state, with energies E1 and E2 respectively. If the atom is in the excited state, it may decay into the lower state by the process of spontaneous emission, releasing the difference in energies between the two states as a photon. the photon will have frequency nu and energy h nu, given by, where h is Planck's constant. Alternatively, if the excited state atom is perturbed by an electric field of frequency, it may emit an additional photon of the same frequency and in phase, thus augmenting the external field, leaving the atom in the lower energy state. This process is known as stimulated emission. In a group of such atoms, if the number of atoms in the excited state is given by N2, the rate at which stimulated emission occurs is given by, where the proportionality constant B21 is known as the Einstein B coefficient for that particular transition, and ρ is the radiation density of the incident field at frequency nu. The rate of emission is thus proportional to the number of atoms in the excited state N2, and to the density of incident photons. At the same time, there will be a process of atomic absorption which removes energy from the field while raising electrons from the lower state to the upper state. Its rate is given by an essentially identical equation. The rate of absorption is thus proportional to the number of atoms in the lower state, N1. Einstein showed that the coefficient for this transition must be identical to that for stimulated emission. Thus absorption and stimulated emission are reverse processes proceeding at somewhat different rates. Another way of viewing this is to look at the net stimulated emission or absorption, viewing it as a single process. The net rate of transitions from E2 to E1 due to this combined process can be found by adding their respective rates, given above. Thus a net power is released into the electric field equal to the photon energy h nu times this net transition rate. Otherwise there is net absorption and the power of the wave is reduced during passage through the medium. The special condition is known as a population inversion, a rather unusual condition that must be affected in the gain medium of a laser. The notable characteristic of stimulated emission compared to everyday light sources is that the emitted photons have the same frequency, phase, polarization, and direction of propagation as the incident photons. The photons involved are thus mutually coherent. When a population inversion, emission will be decreased according to the so-called line shape, considering only homogeneous broadening affecting an atomic or molecular resonance. The spectral line shape function is described as a Lorentzian distribution, whereas the full width at half maximum or FWHM bandwidth. The peak value of the Lorentzian line shape occurs at the line center. A line shape function can be normalized so that its value is unity. In the case of a Lorentzian we obtain. Thus stimulated emission at frequencies away from is reduced by this factor. In practice there may also be broadening of the line shape due to inhomogeneous broadening, most notably due to the Doppler effect resulting from the distribution of velocities in a gas at a certain temperature. This has a Gaussian shape and reduces the peak strength of the line shape function. In a practical problem, the full line shape function can be computed through a convolution of the individual line shape functions involved. Therefore, optical amplification will add power to an incident optical field at frequency at a rate given by stimulated emission cross-section. The stimulated emission cross-section is where A21 is the Einstein A coefficient, lambda is the wavelength in the void, n is the refractive index of the medium, and g is the spectral line shape function. Optical amplification. Stimulated emission can provide a physical mechanism for optical amplification. If an external source of energy stimulates more than 50% of the atoms in the ground state to transition into the excited state, then what is called a population inversion is created. When light of the appropriate frequency passes through the inverted medium, the photons are either absorbed by the atoms that remain in the ground state, or the photons stimulate the excited atoms to emit additional photons of the same frequency, phase, and direction. Since more atoms are in the excited state than in the ground state, then an amplification of the input intensity results. The population inversion, in units of atoms per cubic meter, is where G1 and G2 are the degeneracies of energy levels 1 and 2, respectively. small signal gain equation. The intensity of the stimulated emission is governed by the following differential equation. As long as the intensity I is small enough so that it does not have a significant effect on the magnitude of the population inversion. Grouping the first two factors together, this equation simplifies as where is the small signal gain coefficient. We can solve the differential equation using separation of variables. Integrating, we find, or where is the optical intensity of the input signal. Saturation intensity. The saturation intensity is defined as the input intensity at which the gain of the optical amplifier drops to exactly half of the small signal gain. We can compute the saturation intensity as where h is Planck's constant, and tau s is the saturation time constant, which depends on the spontaneous emission lifetimes of the various transitions between the energy levels related to the amplification. Is the frequency in Hz general gain equation. The general form of the gain equation, which applies regardless of the input intensity, derives from the general differential equation for the intensity I as a function of position Z in the gain medium, whereas saturation intensity. To solve, we first rearrange the equation in order to separate the variables, intensity I and position Z. Integrating both sides, we obtain or the gain G of the amplifier is defined as the optical intensity I at position Z divided by the input intensity. Substituting this definition into the prior equation, we find the general gain equation. It has been suggested by some physicists that stimulated emission from a long-lived isomeric state should make it possible to construct a gamma-ray laser. However, observing such stimulated emission from a long-lived state is futile. Small signal approximation. In the special case where the input signal is small compared to the saturation intensity, in other words, then the general gain equation gives the small signal gain as or which is identical to the small signal gain equation. Large signal asymptotic behavior. For large input signals, where the gain approaches unity and the general gain equation approaches a linear asymptote,